All right, MOBISEC hackers, welcome back. I hope your break went well and you managed to rest a bit. And for today, we're going to be moving on different things. So in the past, we've seen how to take applications, how they work, how to reverse engineer them. But in today's class, we're going to focus on more system security aspects of Android. So how Android tries to secure the running of these applications and how to the Android system tries to secure applications from potentially malicious applications. Okay, cool. So in particularly, we're going to have 3 Dexo slides on Android system security features. This one is about the Android system aspects. In the future, we're going to see more complex features and APIs. Okay, so let's say that it is the first part of these advanced topics. Again, when I say advanced, doesn't mean very complicated. It doesn't mean they're super advanced. It means that this is not just the classic thing that you see in the tutorial how to reverse an Android application. This material tries to convey more, on the design perspective, on the idea behind some APIs and some choices, and how these choices and decisions evolved from the early versions of Android to more current ones. Okay, cool. So we start with a picture that I've already shown at the beginning, and I hope you are now more familiar with what this picture tries to convey. So on the top, we have these applications. Now, if you check the picture, it mentions things like alarm, browser, calculator. These are all apps that are already installed on your app. But at this layer, of course, we find third-party applications also. So applications that you could install from the Play Store or from somewhere else. Okay. So, and as this picture shows, apps usually build on top of the Android framework, which builds on top of the native library. And this Android framework relies on being within the Android runtime to somehow work properly. But again, this picture is nice, but I hope that at this point you know that it's not telling exactly what could potentially going on. So, for example, applications they play on top of the Android framework, which plays on top of the native library. But I guess, it should be clear at this point that an application could directly play with the native code layer and do something there. Okay, so the fact that that's how normally it works doesn't mean that it's always how it works. Okay, so please keep in mind. And again, going through this picture, we have from the native libraries, then these usually they work on top of the HAL, so the hardware abstraction layer, with which you can interface with audio, Bluetooth, and so forth. And this somehow is a generalization of, it's a kind of an abstraction that abstracts away the different details on specific, audio drivers or Bluetooth drivers and so forth. It could be different depending on your phone. Okay, and all these things sit on top of the Linux, on the Linux kernel. Okay, so again, we've seen how you have different apps on a system, and we've seen that these apps are sandboxed. Okay. Now, what does it mean sandbox? It means that in theory, app A shouldn't be able to interact much with app B unless it goes through well-defined APIs and well-defined interfaces. Okay. And I also hope that at this point, again, somehow communications cannot really happen without interacting with the operating system. Okay, so somehow even if you call an Android API, nothing happens in the environment of the Android API and of the Android app A, for example. To actually have some effect of the external world, where external world could be the operating system or another application, these Android APIs usually they somehow invoke some syscall, they somehow interact with the Linux kernel, so that something happens and this something is reflected to the rest of the system. And again, it's very, very important to understand where the actual security kicks in. Okay, so there is sometimes a confusion where basically you have, application A and B are sandboxed, and some people, including Android developers in the past, somehow they put security checks, for example, in the Android framework layer, but they put these checks in Android framework layer that somehow still belongs to the security boundary of application A. Okay, so the fact that you have a security check in the Android framework doesn't mean it's a good security check, because if the application can just call directly what's below the security check, then the security check is bypassed. And believe it or not, this happened multiple times with real Android frameworks itself. So it was not a bug of an application, it was a bug, several bugs, and there are several papers on this topic, or bugs on the Android framework. And basically, sometimes there was a check both on the security space of A and B. So A could be bypassed, but anyways, the security checks on the actual kernel or on the actual Android framework running its system app would be there, but sometimes it was not. And so you could bypass the so-called user space check and bypass the security check. Okay, so this picture and these orange circles try to stress that that's where the real security checks are. Okay, or that's where the real security checks should be. Why? Again, because if you run application A and this application A is not trusted, well, you should assume that this application A could invoke your Android framework, could invoke directly the native code library. So you shouldn't really rely on checks on Android framework that runs on the user space app, on the application A, which is potentially malicious, and so forth. Okay, so somehow in terms of trust, boundaries, you should imagine this picture, not the one before. Okay, so application A somehow can affect the way it wants all code that runs under his user, which again includes some code from the framework, some code from native libraries, some code from HL, and so forth. Okay. Now, the black line, the horizontal black line, is where the real security checks is, or where the real security check should be. If it's not there, it could be bypassed. And another point that I want to make with this slide is that there are many tools and approaches that try to do instrumentation. What is instrumentation? That's what we've seen last time, where basically you try to gather information about the runtime behavior on an application. For example, you want to log APIs. So for example, I want to know if this app is contacting a specific URL or is opening a file and so forth. There are ways to monitor APIs. So you can have the list and all the list of APIs that application is calling, but this is all bypassable. Why? Again, because the application A could call directly, could invoke directly the syscalls that would be provoked by invoking the API X. So if you have API X usually is translated to a number of syscalls. Application A could just invoke the number of syscalls without calling API X. And so all these things that try to monitor, have you called API X, are going to be bypassed. Okay. So if you really want to have a proper instrumentation system, conceptually, this should happen where this green dot line or green dash line is. Okay, that's where the security or security checks or instrumentations really cannot be bypassed unless you have bugs in the kernel and so forth. But assuming a bug-free system, you should not be able to bypass syscall instrumentation, where you basically log which syscalls you are invoking. But again, assuming a bug-free system, it's easy to bypass frameworks like some of the ones we've seen last time. For example, the classic API instrumentation or Frida or Exposed. You can bypass this by just not calling the APIs, just calling what the API would have called. Okay. So the cons of putting the actual instrumentation at this green line, well, the pro is obvious. As I said, you cannot bypass this, at least if there are no bugs. The big cons is that you have a so-called semantic gap. What is a semantic gap? Well, imagine you have APIs and then you have syscalls. You have a bunch of APIs, and APIs names are usually very descriptive. So if you see the API name X, oh, okay, you're doing X. Now, sometimes these APIs really, the implementation of these APIs shows up in a syscall trace with a number of syscalls. And the syscalls sometimes are very generic. Okay, sometimes you have open, write, these are very simple, but sometimes many operations that happen at the API level are translated to syscalls like IOCTL, which is a syscall that is used to implement binder things and IPC communication and so forth. Okay, so the semantic gap is somehow is bringing up the point that if you check the APIs, you can extract some semantic. Semantic is, oh, what is app trying to do? If you go on the syscall level, it could be that you're losing a lot of information, or maybe the information is there, but it's very, very difficult to somehow go from the syscall abstraction point, going back to the API level abstraction point. Again, the idea is that the high level abstraction point is usually more descriptive, carries more semantics. The lower level carries less semantic. And you know, when I say it's very complicated to reconstruct the semantic gap, so going from the syscall to the API, I mean, it's a nightmare. Okay, we had a project a couple of years ago with a student where it was very, very tough project, and the idea was, you know, we wanted to check how some APIs would translate to syscalls. So what we did was to instrument the system. So we took the Android framework source code, and then we modified it automatically so that we would insert functions that would just log. Once you enter an API X, hey, I just entered the API X, okay? Once you exit from the API X, we would just log, hey, we exit API X. And then we did the same with the syscall. And so we would have a long, you know, if you execute an app in this instrumented environment that we created, you would have a long trace with entering API X, entering API Y, entering API Z, syscall A, syscall B, exit API Z, syscall C, exit API Y, and so forth, okay? And from this trace, the idea was to understand, can we really reconstruct automatically? If we see this list of syscalls, then it means that we, you know, the application executed, you know, API X. With the idea being is that in our data set, it's all, you know, we only had benign apps. So we run many benign apps. So we take these traces and so forth. But it is that maybe you have a malicious app, and this malicious app is bypassing the API's instrumentation. But maybe we could still understand, looking at the syscall, hey, we have seen this list of syscalls, and we know that this corresponds to downloading a file from the internet. So we tried, nightmare. It's extremely complicated, and in most cases it doesn't work. So somehow we were able to publish a paper on this. There is a link there, but it's mostly negative resulting. So we describe our attempts to do this. You know, we try to do it in a more, you know, in a very systematic way. The results are very interesting, but it is mostly telling us, you know, it's very complicated, and that's a bad news, right? Because it shows that it's very difficult to go from syscall to APIs. And we point out one more time that all these frameworks working at API level can be bypassed. Again, there is no big news here. The news is that it's very difficult to go back. It could be that other people smarter than us figure it out, but as of now, it seems still an open problem. Okay. Doesn't mean that you shouldn't use Frida or tools that allow you to do API instrumentation. Of course not. You should just take this into account. Okay. So Frida works most of the time. You should be able to see the APIs that are invoked. You should be able to do hooking and so forth. And again, most of the times it actually works. This slide tries to convey, hey, if something is not working, it could be that you found an app that somehow is managing to bypass this. So again, Frida is great. You should keep using it. I'm going to keep using it. If something doesn't work, well, try to monitor for different things. Maybe there is something like this going on. Okay, cool. All right, so moving on. The Android folks had a number of systems, a number of building blocks to build security in Android. And today we're going to discuss these three. So there are some security services offered by Google, and then there is security from security systems perspective done in Android OS, or that is based on Linux. And then there is also the hardware part of the device. Okay. So we're going to have a mini journey in these three aspects. All right. So Google security services. All right. So the first thing is the Google Play. So Google Play is the the store where you can actually download applications, and it's somehow a central part where you can go when you want to download applications, and somehow the developers and the apps on your phone are linked via application signatures. Okay, as we have seen already. And then this the fact that there is a centralized store, this allows to have reviews. So somebody can go on the Play Store and says, okay, this app is great, this app is bad. And since Google has all the applications, they can do app security scanning. So they have tons of resources, they can scan all the applications and trying to find the bad stuff. Okay, so One thing to note is that I'm going to present different layers and different aspects about security. None of this per se is perfect. Okay. Again, if you were perfect, then maybe you wouldn't need all these other layers. So none of this is perfect, but these are different steps in the chain from app developing to the user installing the app and so forth. And each of these has some pros and then some cons. Okay. So if you're wondering, oh, I'd say Google Play, and it's saying, oh, they can do app security scanning, and you're wondering, oh, but can you bypass it? Yes, of course, you can bypass it. Okay, but you're gonna catch something, and you can bypass it, but maybe Google can improve their analysis system, and so it's more difficult to bypass and so forth. So each of these layers that I'm gonna present as pros and cons, don't perceive these slides as, oh, with this you're gonna solve everything. That's never the case. Okay, cool. But again, you should understand at least that having a central place where things, where with the apps you can install are, it's actually, it has some security benefits. Again, if there is some bad app and then somebody flags it, then it's flagged for everybody and you cannot download it anymore. Okay. If it wouldn't be like this, if we just have a bunch of links around the internet, then maybe it would be more difficult to blacklist a specific application for all the users. Okay. There are also security reports. If you're interested to get an idea what kind of bad stuff Google catches on the Play Store or somewhere else, every year Google publishes the year in review, whatever, 2000XX reports. You should be able to find them at this link. And again, these are very big PDFs where they discuss the different trends, different kind of malware, what kind of malware was most prevalent, how many apps they flagged as malicious. Again, it's a very interesting reports. Again, doesn't mean that whatever they say or whatever they try to convey is absolutely true. Well, there is no reason to doubt that the numbers that they report are actually accurate. But of course, how you interpret this number could be seen as could be seen under different lights. And of course, it's up to you to really understand what's going on. Okay. So for example, in the past, they would say, oh, there is just 0.01, that's just an example, okay? They would say, oh, there is just 0.01% of malicious apps on the Play Store, but then you do the math and it's like, there are maybe, the point was 1 million applications on the store, 0.01%, well, it's still big, right? But then the question is, okay, but are these applications that are installed by million users or just random applications? So what I'm trying to say here is there are many resources with information. These security reports are one of them. Try to develop critical thinking when reading these things. You're gonna usually see from security reports from Google, they're gonna try to calm people, say, guys, we have this under control and so forth, and kind of makes sense. But maybe you're going to see blog posts from security companies saying, oh, there was so many malware out there and you really need our product to actually secure yourself. Okay. Again, try to develop critical thinking, trying to develop be with your eyes open, trying to keep into account who is writing this report because they may have specific incentives. Okay, cool. All right, other things. We have bug report and triaging. So the idea here is that if I find a bug, basically I submit the bug to Google and Google is going to fix it and maybe give me some money. I have more details about this process later, but again, the idea is that there is a centralized place where you can submit bugs. These bugs are going to be fixed in the maybe next version of Android, and then eventually there's going to be an update of the Android system and people are going to be protected from these specific bugs. Okay. Another thing is that on Android system, there are different process types. And the kind of process types that you see are constrained processes, underprivileged, unprivileged processes, privileged processes, trusted computing base, we're going to see what it is later, or bootloaders, or trust execution environment. Again, what some of these terms are we're going to discuss them later today. But the idea is that once you submit a bug, Google tries to understand in which category of these processes the bug lies, okay, or the bugs affect. And depending on the type of process, this is going to be escalated internally in different ways. Okay, so that's how the initial, let's say, categorization starts. Then they're going to ask you again. This is still under the part of when you submit a bug, or what was the potential net effect of the bug. One relevant aspect is if it's local or remote. What does it mean? Well, in very shortly, a local bug maybe is more, or you need to assume that you have a malicious app installed on the phone, and then the malicious app can do something bad. While the remote bug would be, I'm not assuming that I have an application already installed on the phone, but I assume only that I need to have your telephone number, and then I send you an SMS and infect your phone. Okay, I have a crazy amount of slides on how to categorize bugs and discussion of trend models and so forth. This is just very, very, very high level view on, hey, if you find a bug, there are many different aspects and to consider, and Google is going to use these aspects to understand how to prioritize them. Okay, so again, we've seen process type, local, remote, and from these aspects, then depending on the bug, they're going to assign a label, which could a label of how severe is the bug is, from critical to low, and again, depending on how critical it is, they're gonna they're gonna deal with this accordingly. Usually, if it's a critical high bug, high severity bug, is gonna be fixed soon, and usually you're gonna get it as soon as there is a security update. How often are these security updates? Well, I have slides on this later. It depends on the phone. For moderate bugs, usually they are fixed, but they're going to be released. They're going to be merged in the next major revision of Android framework. So, at least that's what happened in my experience when we submitted bugs with students. For the moderate ones, maybe we found bugs in Android 9 and in previous versions, and they're going to be fixed in the Android 10. Okay. And many bugs that we submitted in the past were targeted low. Some of them were fixed, some of them were not. Some bugs are more difficult to be fixed, so maybe they don't want to introduce more complexity to fix this low severity bug. Again, I have some notes on this later, but again, you get the idea. Okay, cool. And again, this is somehow is not a service per se, but it's something that Google maintains. Okay, and that's something that Google pushes for Android. Android, there is the main different versions and so forth, but at least where to submit bugs. They keep them into account, they fix them, and then they can eventually these fixes are going to be going through the different Android systems or different Android systems used by different manufacturers, and they're going to reach the end users. Okay, again, yet another technique to secure your phones. All right, so I mentioned a second ago Android updates. Google maintains a system to actually update Android devices. Okay, and nowadays you basically can they are updated via the web, and they are so-called over-the-air updates, or OTA, where basically you don't need to download the file and manually push to your phone, but this is done automatically. Okay, so at some point, depending on the phone and other circumstances, you're going to see in your phone, hey, there is an OTA update, there is an update, and it's automatically downloaded, it's automatically installed, you reboot the phone, the update is there. Okay. Another thing is that there are monthly security updates. That's a recent thing, relatively recent thing, and now it's multiple years. And the idea is that you submit bugs to Google, and then Google collects them, and then every month they release updates where basically they fix a number of bugs, some of which was reported. It's not that I submit bugs in February and then it's going to be fixed in the one in March. It really depends on the complexity of the bug, the severity, how easy to exploit, what are the consequences, and so forth. But again, my point here is that Google tries to push out an update every month. Okay, so every month you're going to see the number of bugs that have been fixed in that release. And again, every month, usually you get an OTA for a phone, depending on which phone you have and so forth. I have a Pixel Pixel is one of these flagship devices from Google, and these guys have top priority. So every month, more or less, I get an OTA. Actually, it is every month, but what I notice is that maybe the update is released on maybe March 5th, and I get the update March 15th. So it is every month, but there is still some delay. Again, we're gonna go a bit deeper on this later on. But again, the updates are out every month. When do you get updates? It depends on your phone. In my case, maybe I get a delay of 10 days. In other case, you may get a delay of months, okay? Again, more on this later. If you're curious about what kind of bugs we're talking about and what kind of security updates we're talking about, well, there is a link. So again, every month, there is a new so-called security bulletin where Google goes through the list of bugs they fixed with the severity, which component they affected. Sometimes they have links to the appropriate Git repository, so you can actually see the diff. You can see the patch of how they fixed the bug and where the bug was. And then, you should have an entry for each of the month for the last 3-4 years. And, it's very, very interesting. All right. So in terms of security bugs, there was a main news maybe a couple of years ago called Project Treble. What is it and what kind of problem it tries to solve? Well, one of the core problems of Android is called fragmentation. Fragmentation means that there are many devices out there, and many types of devices out there. Okay, some of these devices are supported by Google or are, really considered the flagship device from Google. Some others are produced by different manufacturers. Okay, and these different manufacturers, it could be, for example, Samsung. Basically, they take the Android system and they adapt it to their needs, and then they push in their phone, and that's how it works. Okay, but again, Samsung phone is different from maybe my Pixel. And these differences may have security repercussions, okay? And that's what we mean with this fragmentation problem. So fragmentation is the aspect where basically you have tons of different brands supporting Android, and you have tons of different, slightly different versions of Android that are somehow running on billions of phones, okay? One repercussion of this fragmentation is that many devices don't get updated. Since there are many slightly different versions of Android, it's not that you get there is a bug and then there is a patch for bug, okay? And you take this patch, and maybe the patch is simple, okay, you can take this patch and apply it to your code base. But if the patch is slightly more complicated, then it's tricky, okay? And if you just take the official Android source code and you have the patch, you can just apply the patch. Since you took the original Android source code, it's going to work. But if you do some customization, then it's tricky, right? Because you take this complex patch, you apply it, but are you really sure that it's not going to break other things? Okay. And, these customizations create problems because it makes the application of a patch much more complicated, again, depending on the cases. And this process, maybe it happens for newer devices, vendors to go through, okay, we need to take this patch X, okay, we modified this piece of code, let's see how we can apply the patch and so forth. This takes time and takes a lot of money to maintain. So what happens is that usually this process happens for devices in the last 2-3 years, but it doesn't happen anymore for devices sold before that point, okay? And so what happens is that even for devices that were Google sponsored, let's say, like my old Nexus, these guys don't get security updates anymore, okay? And this phone is perfect. The phone still works perfectly fine, but it doesn't get new versions of Android and it doesn't get security updates anymore, okay? And again, it's because there are many slightly different versions of things, and not even Google has time and money to maintain all these different Android devices. Again, this thing, as I mentioned, has security repercussions. And when I say, oh, it's more difficult, it could be difficult to apply a patch on device X because maybe this device X has some customization, this implies that we have potential delays. Okay, because again, this takes time, this takes money, and if I take the patch from Google and now I need to apply internally and now I need to do all the tests and so forth, again, this takes time. So now you have the big companies like Samsung, they do a good job. Maybe I actually don't know details, I never had a Samsung phone, but for Google, you get a patch every month, more or less. For Samsung, it shouldn't be that crazy. Maybe it's going to be 2 months, 3 months. For other devices, it's going to be 6 months. Again, this in the nowadays is much better. In the past 5 years, maybe you get something like every 6 months or every 1 year. Okay, so it's getting better. We are not there yet, but it's getting better. Again, what I'm trying to convey with the slides is not, oh my God, we're all doomed. It's like, hey, there is this problem, there is fragmentation, and I want to convey, try to critically think what this problem, this fragmentation, somehow have security repercussions. Okay, so the idea is that it's an entire ecosystem that needs to work. The fact that there are many versions, you need to understand, hey, it takes time to implement the patch or to test the patch and so forth, and it takes time to actually deploy the patch to the users, and this creates a delay. Okay, so again, I try to convey all these dynamics. Now, one core problem is that, and again, now we go back to this Project Treble. In the past, before Project Treble, there was no clear interface between the Android operating system and the vendor implementation. So, what it means is that you have the Android system, let's say, and then the vendor or this third-party manufacturer will basically do the modifications, but these modifications will be somehow intertwined with the Android framework code base. And now, if there is a patch from the Android people, you need to apply it, and now could be tricky, right? Because this code that was patched could be very intertwined with these vendor modifications, and now it takes time. So again, we're back to the delays. Now, before Project Treble, we could represent the situation in this way. Basically, we have we have Android OS framework on the left, which includes some vendor implementation, and now you need to update it. Well, you get the updated Android OS, but now you need to rework this vendor implementation. This takes time, this takes resources, and this creates delays or brings devices that could have been supported with a better cycle or better way to handle patches that are not supported anymore. Project Treble, this happened in Android 8, so it's like 2-3 years ago. What they try to do with Project Treble is to somehow set a line. And so this is an effort from the Android developers, where basically you have a well-separated Android framework code base, and then you have the actual vendor implementation, and there is a clean interface between the Android framework OS and the vendor implementation. And the idea is that Google would tell the vendor, like, hey, Samsung, this is Android framework, and that's where you could put your vendor modification, and that's where we set the line. And we promise you that no matter what, we're not going to modify, this interface. Okay. So if you actually do this, if you're able to follow all these Project Treble specifications, if you're able to, isolate your vendor component here, and somehow there is an interface and you don't touch the Android framework, well, it's great, right? Because now I'm going to provide you patches for Android, and then you're going to be able to cleanly apply these patches. And we promise you that these patches are not going to bother the vendor interface. Okay. So somehow, myself as a vendor, I can say, wow, this stuff is great, right? If I can cleanly separate stuff, then I can take all the patches from Google, apply them blindly, and I know it's going to work. Great idea. Implementation-wise, a bit trickier, because maybe it's not easy to really separate this vendor implementation completely. And again, it's a great idea in principle, but not all vendors are able to really separate completely this vendor implementation from the Android OS. Clearly, this idea had a good influence, but we're not there yet. We have an upcoming paper with a student at Security and Privacy that just got accepted 2 days ago. So I don't have a link at the moment, but check the slides maybe in 2 months, and we're going to have a link with a paper where we studied kind of a customizations of this third-party manufacturers, or OEM, and we show that it's not as clear-cut as we would have thought. Cool. But again, great effort. Again, the idea is try to get the idea behind this and why this idea makes sense. All right, moving on, we have application services. And there are frameworks that allow Android apps to use cloud capabilities in a simpler, you don't need to implement your stuff. Google somehow has something for you, and if you use this, they're going to maintain the security of it and so forth. And there are some examples. One is the backup service. Basically, it's a service where basically they take care of the backup, and basically they just offer some APIs or some ways to implement this backup, but you don't need to do this yourself. Okay, so they step in trying to help out. So there is one reference implementation. Another idea was this cloud to device messaging. It was called this C2DM, but the current version is this Firebase cloud messaging. Check the docs if you're curious. The idea is that it allows push notification from the cloud to device. So this is useful, for example, if there is some notification that a website wants to send you, somehow there is a trusted way to push this notification to the phone and you get a notification on your phone. Okay. Again, instead of asking developers to implement this channel by themselves, Google steps in, provides a reference implementation or a service, and you can use this service to do your own thing. Okay. Again, the idea here is that sometimes Google steps in and tries to implement services so that third-party vendors or third-party application developers don't need to implement these things that are sometimes often leading to security bugs. And again, try to get an idea on why you need to understand why this stuff is beneficial. If there is one implementation of a service done by Google where there are many people checking it, this is much better than having a custom implementation of this cloud to device communication channel for each specific third-party app. Cool. All right, another service is SafetyNet. So SafetyNet, okay, I think I copied this from their own website. It is a privacy-preserving intrusion detection system to assist Google tracking and mitigating known security threats. So SafetyNet is basically something that runs on your device and check things out and checks that everything is fine. Okay, so it runs on all Google phones, and the idea is that again there are some services, and you can query this kind of system or service running on your phone to check that everything is fine. And there is a thing called SafetyNet attestation, and it's basically an API to determine whether the device is CTS compatible. CTS stands for, well, it doesn't literally stand for this, but we mean the CTS are more this Android compatibility test. And somehow you can ask a question to the SafetyNet service as, hey, is this device okay? And this check could include things like is the device rooted, or is some kind of other weird stuff going on. And it's actually used. For example, if you have banking apps want to make sure that you are not running maybe in a rooted environment, and they just call SafetyNet and they check that the device is actually okay. All right. So it somehow collects a software and hardware profile in a trusted way. Some of these things are bypassable, some of these things are not. If you take the banking application scenario, for example, banking app could call the SafetyNet API to check is the phone rooted or not, or was this specific IMEI of this phone. You can ask a number of different questions, and of course, if you have control of the banking app, maybe you can modify it a little bit so that you somehow fake that the SafetyNet API return everything is good, but actually maybe everything was not good. So you can have tricks like this, but through the power of attestation, which is something we're going to explore better later on, you may be able to actually trust, this value that the SafetyNet is giving me is actually the real one. Okay. So again, depending on what kind of answers you are asking to the SafetyNet API, you can trust it blindly, or sometimes you cannot. But again, it's one more service and one more way to make attackers' life a bit more difficult. Yeah, there's another check you can do with SafetyNet. You can check whether an app has been modified or not. Cool. All right, moving on. Verify apps. So Verify apps is another service that runs on every phone. And it's a system that checks every app that you have installed, and it checks whether that app is malicious or not. Okay. Actually, what it does is not really to scan the application. I guess it takes some kind of form of hash, and it checks whether the app is considered benign or not. If it's not considered benign, then I think Google has the power to stop the app, maybe even uninstall it. And so they basically have some kind of a backdoor. Again, not in a bad way. It's well known that these Verify apps exist, so it's not a surprise. They have a centralized way to say this app is bad, bam, let's kill it. And again, security-wise, it's not that bad, because if it were not for a system like this, maybe or the community knows that application X is bad, but then there was no way to disable this application on these billions devices. Okay. Again, it's yet again another of these service that Google has to try to improve Android security posture, at least on a specific aspect. There is another thing called Android Device Manager. It's basically some kind of a web app and to use when you need to locate your phone, or when you think it's stolen and so forth, or when you don't know where it is. And so it's a web interface. I think I have the link here. Yes. It's great. You can go there, you authenticate, you're going to see all the phones that you registered with your Google account, and you can do play sound. You can do a secure device. You can basically lock it remotely and display a message. You can wipe the device, and you are going to also be able to geolocate it if the location was enabled. So you're going to know exactly where the device is. Again, that's checking a different threat. Maybe it's more the physical security aspect. Maybe your phone got stolen, or maybe you just lost it. You don't know where it is. You can use this system. Okay. So again, and I guess what is coming out from these slides is that there are many systems that are kind of different and kind of covering different aspects of the security, which could go from a malicious app to bugs to physical security. And that's the point, right? These systems are believed to be some kind of complementary. Okay. All right, that was a long ride on this Google services. Please check. Every year there is a new version of Android, and every year they introduce new stuff. So again, these slides are more to present the current status, but this stuff is in evolution. Okay, so the idea is to convey, there are many systems, and that's how Google approaches problem X or problem Y, problem Z in different ways. But this stuff is in evolution, and it could be the next year there is something else. And again, the idea here is not that this information is going to be true forever. The idea is to convey the mindset and the, how different things fit together. And then, of course, the implementation could change over time. But the idea is that you have different kind of threats, and you have different systems that, although they are not perfect, somehow help preventing and protecting users. This is what I want to convey with the slides. Okay, cool. So moving on. The second big chunk of security comes from camera security and Linux. Let's get through it. Cool. So Linux security. As I mentioned many times, Android is built on Linux, and some of the Android security components rely on the security built in Linux. Okay. Linux has a user-based permission model. So you have a user, and then you have an application with a different user. These guys are somehow sandboxed. So you can set up your own folders so that the user B cannot read your own thing. If user B runs something, user A cannot really just see what this user B is doing, and things like this. Okay, and somehow Android relies on this, or uses this user-based permission model by assigning a different Linux user ID to each application. Okay. So once you install an app, a new Linux user ID is assigned, and that's how the basic sandboxing kicks in. Cool. There are also process isolation. So the idea is that, again, if you have two processes, maybe from two different users, it's difficult, or is not thought to be possible, to go from user A process to user B, unless, of course, you find bugs. But if you have bugs, you fix them. But the idea is that Linux is designed so that there is this concept of process isolation. And another idea is that there is this well-defined mechanism for apps to talk together. And again, it's an extensible mechanism for secure inter-process communication. And the idea is that, again, there is one specific way for apps to communicate with the system, or for apps to communicate with each other. And the idea is that once you secure this one, then the entire system benefits from the security. And so, this may seem obvious, but think about if there was not this secure and well-defined IPC mechanism, then maybe you need to have applications that could talk to each other with some, in some other less defined way. And good luck actually securing every possible interaction that this could have. Okay, so having a one very well specified ways for apps to communicate with each other helps designing a system that is not completely flawed. Okay. Of course, the fact that there is a secure IPC doesn't mean that there are no other ways to communicate. Okay. Secure IPC means that there is a well-defined interface, so that if you have application A that wants to talk to application B, well, you need to use this. But of course, the application A and application B are somehow, they want to collaborate and somehow hide that they are communicating. Of course, that's actually possible. If these guys are together and they want to just exchange information without being seen, there are many, many ways. This application A can send something to a website, and then B can download it from the website, or app A can write a file to the SD card, and then file B, application B can read it. It's very difficult to actually understand A is doing this because B is also doing this later on, or A is going to write this file because B is going to read it. This stuff is complicated. This stuff is useful mostly when you have application B that is benign, let's say, and then application A, which is potentially wanting to attack application B. Okay, cool. Again, I'm mentioning this not because it's particularly relevant here, because I'm trying to convey the fact that there is a secure IPC mechanism doesn't mean that all possible communications are secure for whatever definition of secure means. Okay, so every of these things works under the assumptions that the designer of the security mechanisms made, and it's your job and also my job to explain what these assumptions are. And but it's your job to always be critical. You should always ask, what if? Okay, cool. Android, again, builds on Linux, and he also uses Linux capability of removing unnecessary components. So Linux, you have this big kernel, but you have a bunch of modules that implement drivers and different things. And in Linux, you can load and unload these modules. So if there is module or a driver that is usable for some aspect that is not relevant to Android, well, Android can just remove it, and it doesn't ship it, which means you are shrinking the attack surface. If a driver may have a bug, an attacker can actually use it to gain some access to private information. But if this driver is not useful and Android kills it and it doesn't even run it, who cares if there is a bug in driver? Okay, if it's not run, it cannot be attacked. Okay, so this ability to remove unnecessary components has security implications, and whenever you see, oh, I can remove this, it's good news. It should ring a bell. This is good news security-wise, because if something had a bug but is not run or is not there, it cannot be attacked, which means you are reducing the attack surface that is available to the attacker, which is a good thing. All right, so Linux also offers some guarantees in theory. For example, it prevents user A from reading user B files, or if you check Linux design, it is designed to ensure that user A does not exhaust user B memory, or that user A does not exhaust the B CPU resources, or it doesn't exhaust user B's devices. Devices, or aspects such as telephony or the GPS or the Bluetooth or other devices or systems available. This is in part true, in the sense that the Linux on Android delivers quite well on the isolation and the sandboxing component in terms of information sharing. So it's unless you find a bug, it's impossible for a user A or for a process running as user A to read private folder of user B. Again, unless you find a bug. But in terms of isolation, in terms of resources, we are not there yet. So we tried many times to actually check whether it's easy to bring the phone down. So denial of service attacks, where basically you have user A and then you run some infinite loop or some fork bomb or things like this, and usually the phone goes down. I need to admit I didn't check on the latest version of Android. I checked up to, I think, last year, and these tricks always worked. Okay, so it's relatively easy for an application without particular permission to bring the phone completely down and to bring it to resetting it or to bring it to be in a responsive state. It's also particularly easy, or particularly relatively easy, to find denial of service bugs where you can attack a specific system component and bring it down or push it to have an infinite reboot. But these bugs are welcomed by Google in terms of submission, but they are rarely fixed. It's not that they don't care, but I think they have other problems, and fixing some of these bugs would require many modifications. That's my gut feeling. They would require many modifications, and some of these may affect the stability of the system. For example, this fork bomb, the problem is that you should not be able to have a process that can create thousands of processes, and as a consequence, bringing down the system. Well, one solution could be to use Linux capabilities to limit how many processes you can create. This may seem trivial, but maybe implementing it, you may risk to break many benign applications. So, for example, what's the limit? How many processes this user should be allowed to create? I think that if it's difficult to fix these bugs because there are many trade-offs, and denial of service bugs are, depending on the scenario, less important than other classes of bugs. And so that's why at the moment it's relatively easy to bypass this kind of isolation in terms of resources things. But I think that's why we are in this state as of now. So we are not there yet. But it doesn't mean that we're not going to be there for a long time. It could be that security is getting much better. Maybe Google is going to invest resources there. Okay. Also, a couple of notes on this. The importance of bugs really depends on what you're doing with your phones. Okay. So as of now, great, we use it for Twitter, things like this. But looking forward, like in a span of 10 years, what we do with our phones may actually be very different and may actually be much, much more sensitive. For example, there are already proposals to have your device used as a identity card, like an official document, or there are proposals to have your device controlling medical applications, okay, or medical components that are on your body, and maybe the app is the way the interface that the user can say, please do this on the device level, okay. And if we are getting there, maybe denial of service bugs are going to have much more impact, and maybe Google is going to fix them. Okay. So what I'm trying to convey here is, when I say this bug is not very relevant at this point, well, it means at this point. Depending on how the future looks like, depending on what people do with their devices, some bugs that were deemed to be not very important at moment X may be very, very important at moment Y. Again, who cares about mobile security? These are things that are true for security of systems in general. And again, as explained in my first class, my main goal here is to convey mostly about the mindset and the critical thinking than MOBISEC stuff. Okay, MOBISEC is a topic that I like and that I think is still relevant, but maybe it's not going to be relevant in 20 years. But these ideas that bug X could be, maybe it's not relevant now, but depending on the use case, it's going to be relevant in the future. It's going to be, it's a true thing, and it's an important thing to keep in mind. Okay, cool. All right, so another thing was the application sandbox. Again, as I mentioned many times, each app is isolated from each other. And again, each app is assigned to a different user. So this comes for free. By just doing this, by assigning a different user, all these Linux isolation tricks kick in automatically. Okay, so the actual sandbox is in the kernel. In a sense, since the sandbox is implemented through Linux user system, Linux user system, where it's implemented in the Linux kernel, okay? So it's implemented below the interface of the syscalls, which means that even if you don't use APIs, even if you can bypass instrumentation APIs, even if you can run directly native code or assembly in your malicious app, you still cannot bypass the security checks, unless of course you find bugs in the security checks portion of the Linux kernel, but that's a different game, okay? So what I keep stressing here is there were security checks done above the syscall layer and below the syscall layer, below the syscall layer, good, unless you find the bugs in Linux, which is possible, but of course is not trivial. Then you can bypass them. If there were security checks above the syscall layer, these are trivial to bypass because you can just invoke the syscalls by yourself, okay? Cool. Again, to bypass this, you would actually need to compromise the Linux kernel. All right, and this brings me to another topic, or another of this principle that fits well in MOBISEC, but again, in any other security system concept, and it is defense in depth. You're gonna have sometimes multiple layers of security that are there implemented, and they are placed throughout the system, not in just one specific place, but throughout the system, okay? And the idea is that it somehow wants to prevent that a single vulnerability leads to a disaster, okay? And so the idea is I put security check X here and then security checks Y here, and maybe they somehow enforce very similar things. And you may ask, okay, but why is Y important? Can I just remove it? Well, yes, maybe you remove it and maybe nothing happens because X is there. But what about if you find bug in X? Now, if it's only X and you bypass it, then bam, the attacker wins completely. But if you also have Y, it could be that the attacker can find a bug in X, but not in Y. Of course, you need to be smart about this. It's not that just putting two checks is gonna solve something, right? Because if you put two identical checks, if the attacker wins on X, is gonna also win on Y. So the idea here is that you want to have security checks that are maybe done in a different way. Maybe they check slightly different way. Maybe there is some overlap, but again, they try to protect things in different ways so that it's less likely that a bug in X would actually mean that there is also a bug in Y. Okay, so somehow you want to have slightly uncorrelated ways of implementing a check and so forth. And if you want to rephrase it in a layman term, we're talking about redundancy. Okay, so that if there is a bug in something, then the other one is going to save us. Okay, and this brings me to again different security mechanisms. And I start with this defense in depth kind of a concept because what I'm going to explain now may seem something that is not very useful. Because if this, for example, Linux user checks work well, why should I care about XYZ? Or if really everything is the Linux kernel, and if all the checks are done in Linux kernel and the attacker cannot reach the Linux kernel, why should I care about doing also these additional things? Well, we do this because if there is a bug here, maybe this other part is going to save us. Okay, or maybe it's not going to save us completely, but it's going to at least reduce the potential negative impact of a security bug. And again, I have many slides in this slide deck that present the concepts and things that are somehow, maybe not strictly necessary, but in this mindset of defense in depth, where basically we don't want that one bug can bring everything down, they start to make sense. Again, try to keep this defense in depth thing concept in mind. It's extremely important, and you're going to see this over and over and over in every reasonable system security class. All right, enough said. Talk about DEC and MEC. This stuff confuses me all the time. So let's start. DEC stands for discretionary access control. And again, MEC is another thing, but I'm going to present two different ways of implementing security checks or implementing access control. Again, this is discretionary access control. The idea is that each resource has a list of users who can access it, and the permission is set by the data owner. Okay, so Linux file permissions or permissions on a social network fit under the DAC mindset. Okay, why? Well, because I create a file and then I can say, oh, I want this file to be accessible by everybody by changing, you know, the read and write and executable permission for the other group. Okay, social network, I create the resource and then I say I want to share it with X but not with Y. Okay, so again, maybe different social networks give you different ways of saying to which you want to share the post with. For example, Twitter is more like a kind of a binary, like either the tweet is public or you keep them private. With Facebook, I think there is more granularity, but you see my point. You decide to which group you want to share things. Okay. MAC is a different kind of a thing, is a different mindset. MAC stands for mandatory access control. The idea here is that there are a number of levels and each user has a specific level. And a user can access all the resources with a non-greater level than theirs, okay? And this brings me to Selenius context and policies, which we're gonna check in the next slides. But again, the idea is that the system already defines these different levels, and then a given user is assigned somewhere, and then depending on your security level, let's say, then you are able to access X but not Y. Okay. This resembles more what you have with the you know, the classification of documents. For example, you have top secret, secret, and so forth. And depending on your clearance, you may be able to access secret but not top secret, and so forth. Okay, so you as a user, you are assigned to one of each level depending on the clearance, and this level is used to understand, hey, can you access document X or document Y? Okay, cool. So let's talk about Selenius. Selenius is stands for Security Enhanced Linux, and it's a Linux kernel security module. It was there in Android, in Linux already, and is being somehow adopted also in the Android ecosystem. And it's extremely useful to define access control security policies. And again, it's a central role in Android security nowadays. One example is you can say, oh, to this process belongs to this, you assign this context or this level to this process, and you can say, hey, if a process is in this level, then you should not be able to execute syscall X. So you can have policies on what you can execute or not. By default, you have a deny by default, which means that if I do not specifically say that you're allowed to do X, then you're not allowed to do X. Okay. Again, it's like a security by default mindset, where it's better to be clear about what you can do. But if I don't say you can do it, then you cannot do it. And again, in this setting, it's this you should get. It's much better than the opposite, right? We don't want like a block list approach where basically we say, oh, you should not be able to do this and this and this. Why? Because maybe I forgot that there was another syscall, for example, that was potentially abused, and now you can abuse it. Okay, if you can, always having this allow list is much better. Where basically worst case the application doesn't work and it crashes, but at least it doesn't compromise anything. Okay. Of course, it's not simple to arrive to the deny by default policy or to implement it from the start, because you actually may break applications, and you don't want to break applications because then users are mad. Okay, so we have a couple of slides on how the Android folks approach this problem at the beginning, but that's the default, deny by default policy, and you should get why it makes sense. And again, there are two modes for this Linux. One is the permissive mode, which means that when there is a violation, I log about the violation, but I do not enforce it. Okay. And the other mode is the real one, is the enforcing mode, where basically if there is violation, I log it, but it's also enforced. Okay. And again, this permissive mode, you may say, but it's not really, adding anything security-wise. Well, you may be right, in the sense that if you are in permissive mode, the fact that there is a policy or not doesn't matter. The user or the process is still allowed to do X and Y. Okay, but if you keep in mind that the entire context, the entire ecosystem, the fact that there are millions of applications that do crazy different things, and so forth, and the fact that somehow to start with the Linux policy, you need to define what you can do, what you cannot do. And the fact that you have a deny by default, you really need to be careful before saying you cannot do X. Well, permissive mode has been extremely useful, which has security advantages. How? Well, what they did at the beginning is that they enabled this, they came out with a policy and then enabled this in permissive mode, and then they logged what kind of violations were out there, and then they somehow used the data set to understand whether it's okay, or whether we should also allow this, which is not potentially abusive, and also we are not going to break any application, so we should definitely do it. Okay, so again, what I want to convey here is that there are some things that may not seem to directly be security beneficial, like this permissive mode, but somehow the fact that this permissive mode exists provides a way to implement security things in the long run. Okay, cool. All right, so a bit more information about Linux. There is a concept of Linux domain. It's basically it's a label identifying a process or one or more, and all processes labeled in the same way, they are treated as equal. Okay. And in early version of Android, what you had was basically 4 domains. They basically, and then you get all these 4 important aspects of Android. The point install for example, the install driver, also the code is like the init of Android, and so forth. Each of these was placed in our domain, but nowadays there are many more domains. When I did this slide, I think last year there were more than 60, but I think this number is getting higher. Okay, so they started simple, and then somehow they're getting more fine-grained, and they're able to isolate different components in different security domains. Okay. They started in Android 5, and actually Linux was introduced before, but they run it in permissive mode. In Android 5, they start to run it in enforcing mode for the first time, and that's when they started to have separation imposed by the system and the by these Mac policies and the Linux policies between system and apps. Now, this is where the redundancy kicks in a sense that, do you really need Linux to separate system and normal applications? Well, no, because system apps were already run as a different user, as a system user, and third-party applications will be run as each app with its own Linux user. And if everything is fine, these 2 guys should actually be separated. But this stuff kicks in, and now you can enforce different or more higher level policies, and that's where if there is some other bug somewhere else, at least this would offer more protection. Okay. In Android 6, they started to have these policies more restrictive. Again, they logged everything, and so they know, hey, we can basically restrict this aspect a little bit more, and all benign apps are not going to crash, but we potentially could fix and could prevent exploitation of bug X and Y. And so we happen to have tighter domains. We also, in Android 6, we also had IOCTL filtering, where basically the number of exposed services will be reduced. They limit access to /proc, and basically they start to have sandboxes to isolate processes across physical users. So in Android, you can have 2 different users logged in a device, or not at the same time, but 2 different actual physical users. And so you can have 2 different profiles. Maybe it could be your personal life and your work life. And the separation between data of 2 different things will be actually protected not only by the standard permissions, but also from Linux. Okay. In Android 7, what happened is that there was a, I don't know if it was Android 7 or the one before, but basically one of the famous bugs in Android was a stage fright bug, which affected the media server. Media server is this big component in Android that handles everything related to media. So it could be rendering of pictures or audios and things like this. And what happened is that with this stage fright bug, I think it was 2015, is that somebody found a bug in this media server where basically it would send you an SMS or an MMS with the picture, and this picture would be some kind of crafted in a way that it would exploit the bug in media server and get code execution on your device. Okay, Turns out there were a crazy amount of bugs in the media server. So Google is still trying to fix them. It's getting more difficult to find them and so forth. But this took years. And in the meantime, what they did was to take this big media server and somehow split it in different components and somehow protect each component and restrict what kind of actions it should be able to do. So for example, the idea is that if you exploit component X, you cannot really control component Y. That's one thing. Another thing here is in the past, this guy exploited the media server, got code execution, and somehow he was able to maybe open a shell, okay, to execute a different program. But why would a media server that just renders images should be able to start a new process? So what they do is now the process that implements or that runs the media server code cannot do things like this, cannot contact the internet, and so forth. Okay, so again, if you assume the media server is without bugs, this stuff is useless, but bugs are there. And once they're there, this Linux things kicks in and at least prevent that these bugs are exploited in a terrible way. And with these things, or thinking the media server and then splitting in components and then protecting each component, we go to another of these keywords in system security, which is compartmentalization. Compartmentalization, okay? Which somehow, again, tells us you have different components, and if you exploit this one, it's not trivial to go maybe from this one to this one. While if you have a monolithic design where you have one media server, if you exploit this component, well, you're already in the process to also play with this other component, okay? Cool. Android 8, all apps run with seccomp filter, the limit syscalls that they can use. And again, some bugs in the Linux kernel are available because you can invoke syscall X or syscall Y. Well, my baby, syscall Y is not really needed for the Android application. And so what this policy would do is to say, you know what, application X, now you cannot execute the syscall anymore because you don't need it, okay? And so even if there is a bug there, now you cannot really exploit it because you cannot call them syscall. Android 9, each app has its own individual context, and now you are prevented to make your data word writable. In the past, you were able to do it. Maybe it was a mistake of an application, so it was not the default, but you could do this. And if you do this, maybe it will be vulnerable to something. Now it's not the same anymore. Now, do you need to remember all these things and all this evolution? Of course not. My point here is this stuff is an evolution, okay? And so this started 5 years ago, 6 years ago, and then at every iteration, Google tries to have these policies that are more tighter, try to understand, hey, process X really doesn't really need this, so let's remove it so that if there is a bug here, this guy cannot do anything, and things like this, okay? So this also means that you may have tricks on your Android phone that may work now, but they may not work in the future because Google said, you know what, we don't like that apps do this and it's not very beneficial for users anyways. But you know, if there is a bug there, then it's a disaster. So we decided that you're not going to do it anymore. Okay, that was the thing with the access to the /proc. So proc, probably you know it already. It's a special directory where you can access the proc file system, where it's not a real directory backed by the file system, but it's basically a meta directory where you can access system information such as what are the current processes running, how much memory there is, and things like this. And many exploits were actually using information from this /proc folder to make to proper timing for the exploits and so forth. And so Google realized that benign apps should not be allowed to it's not a big deal if benign apps don't have access to this /proc. On the other side, the bad guys were exploiting it, and so they said, you know what, screw it, we're gonna remove access to it. So now you can still access it, but I think the amount of information you can access in this /proc is extremely reduced. Okay, cool. All right, that was a long run of these Linux kernel things. And again, these are just overviews of the different things. It's not super exhaustive, but I think we covered a lot of ground. And the next topic is boot and verify boot. So let's get to it. All right, so the system boots in stages. So first of all, what do I mean with boot? With boot, I mean you know, the phone is off and then you start it. And then there is a process that somehow starts something and then starts something and then starts something, and then your Android device is completely booted and you can start logging in and use your own applications, okay? And again, the system works in stages, and the idea is that each stages loads the next one. Okay, so we start, for example, with the bootloader, and then the bootloader tries to understand what it should boot. Okay, it finds something, great, it loads it, it jumps there. This guy said, oh, what should I boot next? Then it finds something, loads something, it jumps there, and so forth. The aspect that is important security-wise, this verifies the next one. Is this verify boot kicks in when the step one, before randomly loading and jumping to step two, actually checks that step two is somehow legitimate. What is legitimate? Well, the definition may change or may be different depending on the context. And of course, I'm gonna show or define better what it is in this context. But you get the idea. Step one, check something about step two. If everything is fine, it loads step two and it jumps there. Step two does the same with step three, and so forth. And at the end, you're going to have your own Android system. Okay. All right. So in Android, or also in iOS and in different systems, you start with the boot ROM. ROM stands for read-only memory. So this is something hard-coded in your chip in your phone, and you cannot change it. Again, the name read-only memory. And the idea is that this boot ROM, it's a program. So once you start the phone, the processor starts executing code in the boot ROM, and this boot ROM is going to try to find the what's called the security bootloader, SBL, and is going to load it in memory and jumps there. Okay. And you can change this. Okay, so there is a procedure to change it. This is different from the ROM, which you cannot change. And the idea is that the boot ROM, before loading and jumping on this secondary bootloader, it checks cryptographically that this SBL is valid. What does it mean? Well, basically in the ROM, not only there is code to load the SBL and jumping it, there is also a cryptographic key. It's a public key stored in the boot ROM, and what it does is basically loads the SBL, and then it checks that this SBL as a signature, a cryptographic signature, and it checks that this signature actually corresponds, has been signed by the private key associated with the public key are coded in the ROM. So the SBL you have in your phone is of course signed properly. So it has been signed with the private key associated with the public key that is hard-coded on your device. And, I said that you can upgrade this SBL, but if you try to push your own SBL, well, since you don't have the private key that somehow is associated to the publicly hard-coded in the ROM, then you cannot produce a valid signature for SBL, and so the boot ROM would refuse to load it. Okay, and that's where the verified boot kicks in. So to rephrase it, it loads SBL, it reads the content, it tries to verify. So the SBL needs to have a signature. It verifies that the signature is basically produced by the private key associated with the public key hard-coded in the ROM. If it's verified, then great, the code jumps to the SBL, which is now considered trusted. If it's not trusted, then it stops there. Okay, cool. And now the SBL, what it does is to try to find a so-called Android bootloader, also goes by the name of A-boot, and it does something similar. It checks whether this A-boot partition or A-boot content is signed with the key stored in the ROM. If yes, great, it jumps there. If not, bam, it stops there. Okay, and nothing happens. That's it. So the key point here is that this key is hard-coded in the ROM. So if it wouldn't be hard-coded in the ROM, it would be somewhere on your file system. What you could do is to modify the private key there, and then you put your own private. If it's a in the ROM, you store the public key, never the private key, of course. You will store another public key associated with the private key that you own. You sign your own version of a boot, and then this will match. So no, of course, it's not like this. The public key that is considered as the trusted one is in the boot ROM. Okay. Okay, and so now you see that basically we are at the point where basically a boot is also considered trusted, and it's not a boot ROM directly checked that a boot is trusted or not. It's just there is a chain, and this is a two-stage. There are two stages, and so indirectly you can consider the boot trusted because the SBL checked it, and SBL was checked by boot ROM. I guess I'm talking too much for this quite simple concept. All right. We would call this boot ROM and the public key stored in the ROM as the root of the chain of trust. Again, the fact you have multiple stages, you can define this as a chain, and the root of this chain is in the part that you cannot change, is in this boot ROM. Okay. Now, once you are at a boot, basically a boot finds somewhere in the file system the Linux kernel, and it loads it and it jumps there, and then the Linux kernel somehow starts the init RAMFS and then the Android framework. The Android framework then starts other things, which eventually start the system apps, which eventually you're gonna be presented with your, put your pin here. If you put your pin, then the last part of the third-party apps are gonna be started, and that's your phone, and that's how the boot works. Okay. Now, there is a term that goes around in these Android phones or iOS, which is, you can unlock the bootloader. Not in iOS, but in Android, you can unlock the bootloader. So what does it really mean? Well, once I tell you, you can unlock the bootloader, or the bootloader is unlocked, this usually refers to unlocking a boot. Okay. What does it mean? So unlock bootloader means the following. If the bootloader is unlocked, a boot will not enforce the chain of trust over the subsequent stages. Okay. So what also means is that if the bootloader is locked, a boot will absolutely enforce the chain of trust over the subsequent stages. So, for example, going back, a boot will not start an untrusted Linux kernel or something not signed or in a way that the A boot expects. If the A boot is unlocked, then it's going to allow this. And that's how you can install custom mods on Android. So maybe you're familiar, maybe not, but on Android, you can actually replace the official Android system with different versions of the Android system. So there are custom mods or mods of the Android system. So you can have slightly different things going on with your phone. And there is a big community around this. And basically, in that case, they would actually modify the basic Android system that is actually run. And the way you can actually push your own custom Android system is by unlocking a bootloader. So a boot remains the same, but then you can modify the Linux kernel. And since a boot now is unlocked, a boot is not going to complain much that, hey, this component is not exactly what expected, but fine, I'm going to do it anyways. Okay. Note, a boot itself cannot be changed. Or more precisely, you can, but if you change it in a way that is not expected, then the SBL, which is the stage before, will not load it. So while you can push a new version of a boot on your phone, there is a very high risk of breaking it completely. Breaking is when basically your phone, you basically cannot do anything. You cannot do anything anymore. You cannot flash a new clean, version of something. You cannot do factory reset, and so you can return it to the manufacturer. Okay, maybe they have a way to fix it, but that's what we mean with breaking. If you put some random bytes in a boot partition, I think you can, but again, the SBL is going to check the signature of a boot. Is not going to be a valid signature because you don't have the private key associated with the public key in the ROM, and then your phone is doomed. Okay. So again, if I ask you, can you change a boot? Usually the answer is yes, but you cannot really change it in a meaningful way. But at least you can upgrade it. Okay. If you have a new boot signed from Google, is signed with the proper key, then you can push a new version. And again, same for the other partitions. You can modify boot, you can modify system partitions. If a boot is locked, a boot is going to try to enforce the root of trust, the chain of trust, and maybe your boot is not going to be valid, and so your phone is not going to be booted properly. Okay. Yeah, that's what I said. Cool. So I refuse to load them. Okay, another thing to keep in mind is that not all devices allow bootloaders to be unlocked. So on iOS, community is famous so that Apple gives you the device, but you cannot really unlock the thing. And that's why you have things like jailbreaks that somehow allow you to escape the sandbox from Apple and somehow put whatever you want on your Apple device. For Android devices, it really depends. On devices like the Pixel or the Nexus, you can unlock the bootloader. And that's great. In other phones, you could unlock the bootloader in the past, but nowadays it's more difficult. I think in the, for example, recent versions of Huawei phones, it's complicated to. I don't think you get a device you can unlock, at least in an easy way. So again, depends on your phone. Another important thing is fastboot. So fastboot is a tool / protocol for writing data in the device memory. Okay, and that's the tool we use to flash a new a partition with new content. And you can use fastboot in a similar way that you use ADB. So you can do fastboot devices, and you're going to show a list of devices through which you can interact with fastboot. And you can launch commands like this: fastboot flash system image. This means please flash the system partition with the system.image bytes. Okay, so system.image will be a file on your file system, and then you want to put these bytes on the system partition. Okay, yep. So fastboot is a command, right? And if you run it on your laptop, you run it, but then there should be some other component on your phone that somehow interprets the commands from the laptop and do something with it. Okay, it's not some magic stuff that you take some stream of bytes from the system.image and these bytes are copied in the system. No, there is some component on the phone that reads, this guy is talking to me in fastboot way, and it's telling me to flash system.image in system. Okay, I'm gonna do it or not. This fastboot is implemented in a boot. Okay, and that's another way of saying, pay attention. If you screw up a boot, there is no fastboot there anymore. If there is no fastboot anymore, you cannot flash anything else anymore. Okay, and your phone is bricked. And another point here is that's why flashing a boot with some random stuff is very dangerous, but flashing maybe boot or system partition with some random stuff is less dangerous. Because even if you do this, if you flash some random stuff with boot or system partitions, usually you still have a boot, and you can please tell a boot, hey, can you please flash this other thing on boot, so you don't lose access to your phone. Okay, you can flash new things. Okay, so now I mentioned about this unlocking bootloader. How does it actually work in practice? What you can do is to boot your device in bootloader mode. What does it mean? Well, you take the device, it is off, and then usually you press the power button and the device boots. Okay, this is booting in normal mode. Okay, there are different ways of booting your phone, and one of these ways is the bootloader mode. Bootloader modes mean that you start the device and the device is going to stop at the very, very beginning without loading the Android framework. And again, this mode is called bootloader mode, and that's where basically your phone becomes is in a state where you can issue fastboot commands. Okay, so the first step, start your phone in bootloader mode. Technique one is press the power and volume down button while booting, and you're gonna see that your phone is not gonna boot on your normal Android framework and system apps and so forth, but you're gonna have some kind of weird image of the Android logo. And again, there is a special menu there that are going to appear, and then with the power up and down, volume up and down, you can select what you want to do. And the other technique is to you can do something like, they say that the phone is already booted. You can do ADB, which ADB works when the phone is booted normally. You can do reboot bootloader. Okay, so this tells you please reboot, but when you come back, please come back in bootloader mode. And once you're there, you can do, once the device is booted in fastboot mode, you can launch this command: fastboot flashing unlock. Now, this slide should come with an asterisk, because if you take a Pixel 3 from the box, you cannot really do this. There is another step you need to do this, and it's explained in a following slide. But in terms of fast boot, that's actually what's going on. Okay. And then something appears on the screen, and you do confirm to lock. So there are also additional security mechanisms to prevent that an attacker can do weird stuff with these unlocking things. First of all, device data is wiped upon bootloader unlock. So once you do the unlock, usually the device is completely deleted. Okay. And that's done in a way so that if somebody managed to steal your phone, and if somebody's managed to somehow go through the unlock mode, it cannot just do unlock and then take a modified version of Android and then push it there and then use the modified version of Android to steal your data. Okay, so again, security mechanisms so that the impact of a potential unwanted unlock is not as dangerous as it would be without wiping the data. Again, this scenario may be relevant when somebody steals my phone. And if somebody steals my phone, I'm upset because I lost my phone. But in many cases, the more important thing is that I don't lose access to my data. And data is not just my pictures. It could be authentication tokens for my Google account and things like this. Okay. And again, when I describe these kind of security features, always try to think what would happen if this security feature wouldn't be there. Okay, so this is the critical mindset kind of thing I'm talking about. All right, so when it's unlocked, another thing is that the bootloader shows a warning to the user every time the device boots. So let's say that I managed to unlock the device. Once I boot the phone is going to warn me, you know what, pay attention, because your bootloader is actually unlocked. And it's interesting because this happens no matter whether you modified your Android system or not. The fact that the bootloader is unlocked means that potentially somebody has modified it, or potentially you could modify it or not. And it's a very important security aspect of Android. And really, they want to make sure that if your bootloader is unlocked, the user knows once you boot your phone. Okay. Again, if the user is the one that initiated the unlocking procedure, okay. If not, that's a huge warning sign. Okay, at least the user has a way to notice. And then you may ask, oh, but what about you unlock it and then you modify the system so that this warning is not shown? You cannot do this. Why? Because this warning is done in the A-boot part and you cannot change it. Okay. Oh wow, I didn't even know I wrote this. Great. So again, it's an A-boot, you cannot change it. Cool. Other things. Okay, this connects to what I said before, that you cannot just do this and then run fast boot unlock things. Otherwise, actually, it would be pretty easy to do some pranks, right? I steal the phone of my friend, and then I connect it to my, to my laptop. I reboot it in bootloader mode, fast boot, unlock, bam, I wipe his phone. Okay, so I know I cannot do this. So if I buy a new Pixel, there are some protections mechanisms, and again, this applies to Pixel, applies to Nexus, applies to other phones. There is in the settings a thing called allow OM unlocking. That's in the settings on the settings app. So you need to have your phone unlocked. And again, I'm not talking about the bootloader. I'm talking about you take the phone, you start it, you need to put the pin, or if the phone was already started, you need to put the pin or the fingerprint or something like this. And then you can go in the settings and you can do allow OM unlocking. If you don't do this, you cannot really do any fast boot unlock from outside. Okay. This allow OM unlocking, at least on Pixels, is it's in developer options, hidden menu. If you never play with it, it's actually pretty fun. By default, you don't have any developer options item in the settings app, but what you can do is to go to settings, system, about phone, and then there is a build number item. You click, I'm not kidding, you click on it 7 times and this is going to unlock the developer options menu. Now you can click on it, you're going to have a number of different things. And there is also allow OM unlocking. This sometimes I actually think they ask you again your PIN to make sure that is actually the real user of the phone that is trying to doing the OM unlock. And then after this, you can basically set you can basically do what I said before. You can basically start again. You reboot the phone in fastboot mode, and then you do fastboot flash and so forth. Okay. This developer options is also where this allow USB debugging option is. And if you don't do this, if you don't enable this allow USB debugging, you basically cannot you cannot even, you can connect the USB cable, but you don't see it with the IDB, okay, or you don't see it with the fastboot. So these two things, they should be both done in order to actually do what I'm describing now. So again, they try to set the bar very, very high. They try to make sure that in order for an attacker to, or for somebody to unlock the phone, you need to go through the settings and do OM locking. They ask you the PIN, the phone needs to be unlocked. They need to, and then you need to reboot it and so forth. And then even if you do it yourself with all the security things, they also wipe your data. Okay, so they really try to make sure that there is no sensitive user data with the bootloader unlocked without the user noticing it. So this means that if somebody steals my phone, they still cannot do much, because by default, of course, they don't have USB debugging. I don't have OM unlocking. And this means that, if you steal my phone, good for you. But my data at least is not at risk. You cannot use this unlock procedure to bypass security and read all my data. All right, there is another concept related to this bootloader and unlocking and locking things called device state. The device state indicates how freely software can be flashed to a device and whether verification is enforced. Let's go a bit more deeper on this. There are two states, fantastic names, locked and unlocked. Locked means that, again, it's a state, okay? So once you boot the phone tells you I'm in state locked or in state unlocked. State locked means that the device boots only if the operating system, so Linux, kernel, Android, blah, blah, is probably signed by the root of trust that is in the boot run, okay? And it is unlocked, of course, if that's not the case. So basically, once you unlock your bootloader, you still can see what device state you are currently in. And actually, no, I think I said something incorrect. No, basically, this tells you whether you can load something that is not trusted by the root of trust or yes. Okay. Cool. All right. So again, in terms of root of trust and trusting things and so forth, there is another thing. It's called the verity. The verity, again, we're moving away from this boot stuff, but somehow you're going to see how it's related. It's a kernel feature to provide transparent integrity checking of blocked devices. So like, a hard drive. And somehow what they do is to maintain a cryptographic hash of the content they expect to have there. And somehow they go from the actual, layer 0, say, the actual bytes, and then they build an hash starting from small blocks, and then they keep doing hashes and hashes and hashes, and then they basically have the root hash. And then this kernel feature maintains this tree hash at runtime and try to check whether something in the in the system partition, for example, has been modified. And if yes, it blocks the device and it warns the user. Okay, so this is more a runtime kind of a check. Another thing is the rollback protection. Again, somehow related to flashing new things, and you're going to see in a second why. Rollback protection is the following. Is try to protect from the following problem. What you could have is that you have an Android version that is signed properly. And so if you flash it, it's going to be trusted, okay, because it's signed properly. And then let's say that there is a bug in Android version X, okay? And then Google arrives and then fix the bug, and now there is Android version Y. And now there is, of course, Android version Y is also properly signed. Now, one problem is the rollback attack, in a sense that what an attacker could do is to take the phone and then flash Android version X, even if the phone had Android version Y, And the attacker does this because Android version X is known to have a bug maybe inside, okay? A bug an attacker can exploit. And the problem here is that Android version X is probably signed. So if you just check all the I've said so far in terms of root of trust and checking the next stage and so forth, every of the checks is gonna succeed because this guy is actually gonna side with a legitimate key. Okay. Rollback protection tries to, so okay, that's bad because now you're gonna have an old version with a bug inside and the malware could do something bad. Rollback protection is a technique or a mechanism that tries to prevent this problem. And basically what they do is to, let's see if I have it. Okay, that's what an attacker could do with this rollback attack. You could install an exploit and so forth. Rollback protection basically somehow stores somewhere what is the most recent version that the device has seen in terms of Android, and he absolutely refuses to boot an older one. Okay, so what it means is that, let's say they have Android version Y, and now attacker comes and put Android version X. There is a piece of code that is checking that the current version of Android, independently from whether it's trusted or not, is actually a version that is Y, at least Y or a later one. If it's something earlier than Y, then the device refuses to boot. Okay, and so this trick doesn't work anymore. All right, so topic on flashing new image. Basically, the Android phone has a bunch of partitions, and each partition can be flashed with new data. For example, this command we've seen before was to flash the system partition with the system.image file that you have on your machine. But you can do this with the other partitions. And you may ask, where do you get the system.img? Well, there are factory images that Google gives you for all their phones, and you can download it. And there is also a flash-all.sh script, and this script does something like this. Basically, he flashes the bootloader partition, reboots it, and then he flashes the radio partition, and then he does this, this fastboot flash radio bootloader, whatever. That's a command line way to flash this radio bootloader.img file in the radio partition. And then at the end, you have this fastboot update.zip. The way it works is that in this zip, there are a bunch of partitions, content. And so what this fastboot update command does is to open the zip and somehow flash each partition with each of these files inside. And it finds the name of the partition depending on the name of the file. For example, if you have boot.image, it's going to flash boot.image in the boot partition, vendor.image is going to be flashed in the vendor partition, and so forth. Okay? So again, and these one are somehow the names of the various partitions that are on the phone. Again, I think these slides, the bullet was for the Nexus. This doesn't mean that all versions of Android have exactly this partition's name. What you need to get from these slides is the idea, what's behind. Oh, there is a file system, there are a bunch of partitions, you can flash each of these and so forth. You can take the factory images from Google for Google phones. Maybe you can find the same stuff for Samsung phones and so forth. Things like this. It doesn't make any sense to remember exactly what specific name of partitions they have because this stuff changes many times, okay? Again, a bit of deep dive in the partition things. We have the boot partition, which contains the kernel image, and the RAM disk. It's a small partition with things useful to start everything. Then there is a system partition, which contains everything that is mounted under the /system. This includes the Android framework itself or system applications. Then there is the vendor partition. This thing is not part of AOSP, so the Android open source project, and it's actually intuitive why. This vendor is where the vendor customizations kick in, okay? That's not part of the Android open source project. Then there is user data. This partition contains everything about that is in /data, and this is all the third-party apps. These usually live in /data/app/whatever, as we've seen last time, and also their private data. So usually data of these private apps lives in /data/data, whatever app name and so forth. So user data contains this kind of stuff. There is the radio partition. This radio thing is super sensitive, is the one that actually talks to the baseband and provides functionality like internet, phone calls, and things like this. So there is a specific partition for this, and this thing actually runs with its own processor, so it's very, very sensitive. And that's actually interesting. There is a recovery partition, and basically this recovery partition is like boot, but it's for recovery mode. What does it mean? Basically, once you started your phone, you have two different ways of booting things, and two different modes. And so how can you choose which one to use? First of all, well, you go to bootloader mode, which is what we've seen before. And then you choose, basically you can, there are two options in this menu, and it's either start or recovery mode. If you do start, is the normal mode. Basically, the system that you used to know, you start the Android system, and then there is a login screen and things like this. Okay. And the process is, if you do start, you start the normal mode, which means you jump to the boot partition, which is going to start the system partition, which is going to start the vendor and user data partition, and so forth. Okay. In the recovery mode instead, what you do is that instead of using the boot partition, you're going to use the recovery partition. Okay. So by default, this recovery partition is somehow empty, in the sense that you go there and there is nothing. Yeah, I mean, it's not there is nothing, but it doesn't allow you to do anything. If I, whenever I went with my Nexus phone, usually you would see like some Android logo with the guy with open heart or something like this, but you cannot do anything. But with the commands I've shown you now, basically you can flash specific partitions to this recovery partition, and in a way that you have some tools to do something, some kind of admin operations and things like this. So long story short, basically the bootloader allows you to start in normal mode and recovery mode, and it's very very simple procedure, in a sense that the normal mode starts with boot, and then boot does its own way. Recovery mode starts with the recovery partition. Okay, and depending what you put in the recovery partition, you're gonna have something interesting or not. To do this, you need to have the bootloader unlocked. Okay, so if the bootloader is locked, you cannot flash anything there. That's also very important. In terms of recovery partition, what would you want to flash? Well, if you need to do some weird experiments, root your device and things like this, it's frequent to use a project such as Team Win Recovery Project. Basically, it's a project that allows you to have a custom recovery image, and you can go on this website, you can download the proper recovery image that you need for your device, and then you can basically flash this image you download from this website through this fastboot flash recovery command line thing that I hope is clear at this point. It simply takes the bytes that you have in this twrp.image file and puts them in the recovery partition. Now you can start your phone and you select the recovery mode. Now you're going to jump in this partition, and you're going to have an interface like the one I've shown in the picture. Okay, and you can see you can do install things, or mount things, backup things, and wipe things, and so forth. Some kind of admin stuff. Okay, cool. All right, protection of system partition. So the system partition is very important in Android, and again, it contains the Android kernel, the operating system libraries, the application runtime, the framework, and all the pre-installed apps and system apps. Okay, so it's very, very sensitive. And in recent versions of Android, the system partition is read-only. So this is done in a way that if you attack the system and you somehow, even if you are allowed to, if you get some write access to a system directory, in the past you could write something there, and in this way you would achieve persistent, because whatever you write there is going to be started at boot. But in recent versions of Android is mounted as read-only. Does it mean that it's impossible to write something there? Of course not. Maybe there is another bug that allows you to remount a partition as also with not read-only, but also read-write. But you know what? You need to find another bug. So this is yet another case where you have things like, maybe it's not really needed, but it's needed because we want another redundancy, another redundant check. And even if you can do X, and maybe we don't know how you could do X, but even if you can do it, then you still don't win. Okay. Again, in this case, I hope you see the point that achieving persistence for malware is very, it would be very bad for the user, because after this, you can reboot it, you can install your application, you can uninstall your malicious application, but the attacker is there. And once you reboot the phone, the attacker is going to still be there. So it's very, very dangerous. And that's why there are many, many checks in place, many of which are somehow overlapping, or maybe they're not strictly necessary. Because again, you cannot write to system. So why mounting it read-only? You see the point. So we're going to defense in depth. Another interesting aspect is this mount remount is done via syscalls, and maybe through Linux you avoid that a specific component. Mount remount is not that many components need to do it. So somehow the fact that you will need to remount can be blocked via maybe Linux policies. And Linux policies are implemented in different ways with respect to basic file system permission. So you basically have two different things implemented in two different components. And these components maybe are not very correlated, which means that finding a bug in X doesn't mean you also find a trivial bug in Y. And that's why it's a good system. Okay. Again, defense in depth, kind of redundancy check, safety nets, these are all synonymous. Cool. Again, that's what I said before. That's preventing persistence. There is another thing about persistence that is safe mode. So at the beginning, I think I mentioned something like the on-boot completed intent filter, where basically if an application specifies on-boot completer intent filter, then it will be started at boot. And if you think about this, it could be considered as a form of persistence, in a sense that you start the app, you play with it, or you realize it's bad, you stop it, or you stop using it. Now you reset the phone, and now this bad app is again back. Why? Because you had this on-boot completed intent filter, and the app was woken up by the system. Okay. Now, in the past, I also said that to avoid that there is an infinite loop, in a sense that to avoid that the user really has no way to stop the app, the way it works is that if you go to the settings and then you go to the settings of this application and you do force stop, after you do force stop, this on-boot completed mechanism doesn't kick in. So after you do force stop for an application, once you reboot the phone, even if the app had the on-boot completed intent filter, is not going to be woken up. And again, it's done so that a user has a way to stop this malicious app who keep popping up. However, there is a more aggressive scenario where it's very tricky to do this force stop. There are some malicious apps that what they do is when they start, they block the user interface, for example, completely. And if they block the user interface completely, then it's very difficult for the user to go to the settings app and somehow go to force stop. And if the user cannot do force stop, well, it may be game over, because if you stop if you close the phone and then you close, if you turn off the phone and you turn it on again, on-boot completer kicks in again, bam, the app is still full screen, you cannot touch anything, and you're doomed. And that's where safe mode kicks in. So somehow there is a way to start your phone in safe mode. And safe mode means that, to do this, usually it's a press device power button plus volume down. And then you're going to be in safe mode. Again, the specific procedure depends on your specific phone. Google for it. The key point here is that third-party apps are not started automatically. So once you start your phone in safe mode, no matter what kind of settings, no matter what kind of on-boot completed trick or other tricks, third-party apps are not started automatically, which means that no matter what, the user is going to have a way to go to settings, go to the specific app, and doing force stop. Okay, so this safe mode is there so that you avoid that the user, that the malware can get persistent to this on-boot completed or other techniques, and so that if the user somehow is not able to do force stop, at least you can go to safe mode, and then you can uninstall the app before starting it, and now you're safe. Okay, so keep this in mind. Yeah, and of course, it doesn't mean that you cannot run third-party apps. It just means they're not started automatically so that the user can do whatever he wants, and you can start these apps manually. Okay. Cool. And it prevents some form of user space persistence. Another thing, we are approaching the end for today. So, I know I covered a lot of material, but we're almost there. We have seen this picture before. And one question is, what if there are bugs in a boot? So if there is bug there that somehow allows a bad actor to do something bad, that's pretty bad, right? Because if there is bug there, I can just maybe attach my USB cable, do something bad, and now I get access to the entire phone. I can somehow bypass the locking and locking mechanism because that's implemented in a boot, and so forth. So that's very bad. But what's even worse is if the bug happens in boot ROM. So in a boot, the bug is very bad, but you can update it in a sense that that's a boot is stored in a par where you can just modify it. So of course, maybe it's a complex procedure for a normal user, but potentially it can be updated. However, if you find a bug in a boot ROM, then you're really doomed because the boot ROM is not modifiable. It's read-only memory. It's hard-coded in your chip, okay? And so if you find a bug there, there is nothing you can do. And your phone is doomed to be exploitable, okay, depending on the exploit and so forth, okay. And that's why finding a bug in boot ROM is like the holy grail of finding bugs somewhere in phones, because if you find a bug there, there is nothing that the vendor can do, Android, Apple, and so forth, to fix it. There is absolutely nothing. The phone, you cannot patch it. And if you keep using this phone, you need to agree to have a phone that is bugged. And an attacker can just do something and do something bad, okay? Now, these boot ROM bugs are extremely rare, but actually they still happen. And so last year, I think the day before I prepared the slides, there was a checkmate exploit for iOS being released and announced. And this basically, it's extremely cool bug, and they found it in the boot ROM. And this is basically unpatchable in the sense that Apple cannot do anything, and nothing much they can do. All phones with this specific version of the boot ROM are going to remain vulnerable forever. Now, it was bad. It was not it was super bad and super interesting. This was not affecting the latest versions of Apple phones. And actually, so basically in the latest version of Apple phones, there would be a patched version of boot ROM. And actually, this patch was how the researchers that found the bug. So what they did was using a technique called patch diffing. And so basically, they took the latest version of boot ROM, they compared it with the previous version of boot ROM, and they found that something was modified. And this modification, he discovered, was due to a bug being fixed. And so this researcher with other people basically found the bug, discussed the bug, and somehow found a way to exploit it. And he enabled unpatchable jailbreak for all these iOS users with the specific versions of phone with the buggy ROM. And again, nothing much that Apple could do. These phones are going to be jailbreakable forever. Okay, so again, I'm mentioning this because not all bugs are born the same, depending where the bug is, depending if the bug is accessible to the attacker or not, how easy it is accessible to the attacker or not, but also depending on how easy or difficult it is to patch, bugs can be more relevant or less relevant than others. Again, I have tons of slides on try to understand which bug is worse, so kind of threat analysis and threat modeling and things like this. But I just want to give you a glimpse of what kind of trade-offs and what kind of mindset you need to develop to understand, hey, this bug is actually very important, I should pay attention to it, or oh, this researcher is bragging about bug XYZ, but this guy is probably bragging too much for nothing. It's not a big deal. You should be able by the end of this class to create an informed decision, an informed opinion on this bug is relevant for these reasons, and this bug is actually not very relevant, it's just hype. Okay, cool. All right, moving on different systems of protection. there is a data encryption component. So data encryption, super important. The idea is that user-created data are encrypted before writing to disk. Again, think about a world where this wouldn't happen. And of course, this was the case up to 5, 6, 7 years ago. Okay, so you have a device and then you write data and this data is not encrypted. What does it mean? It means that if I lose my device, somebody could extract the files, the disk, and somehow read the content, and this is all my data. So I just need to lose my file, and this guy is going to have access to my photos, my information, my Google authentication tokens, and things like this. Horrible. So in recent or not so recent versions of Android, there is that encryption. We want to store data of the user encrypted before writing into disk, so that if I steal the phone, if I lose the phone and so forth, an attacker cannot just get the actual hard drive and see the data and see my photos. Okay, it's all encrypted. Now there are many ways of implementing this, and with different pros and cons. In Android 5, we start to have full disk encryption by default. In the past, this encryption was only affecting some files, but in Android 5 we have full disk encryption, which means that the entire hard drive is encrypted. And the idea is that there is a single key that protects the full disk encryption, and this single key is protected by the user device password. Okay. What does it mean? It means that there is a key somewhere that can decrypt the entire thing, and this key is unlocked only when the user inserts the password. Okay, and this key is not there in clear. This key somehow is decrypted, let's say, from the user device password, and that's why once you start your phone, from scratch, it always asks you for the PIN. While maybe if you lock it, maybe you have a phone with a fingerprint, you can just put the fingerprint. But if you reboot it, you cannot just put the fingerprint. You need to put your PIN. That's because you need to unlock the full disk encryption, which is unlocked by your password. Okay, so that's why you must provide your credentials upon boot. And there are some problems. Okay, and that's why and these problems, that's why these problems led to different trade-offs in terms of how to implement this full disk encryption. UX problems, so user interface problems. The problem is that if you implement this the way I described it, you start the phone, and then before I put my password, nothing works, not even alarm clocks, and that's very bad, right? Because if I have my phone, now I need to pray the gods of technology that my phone is not going to reboot during the night. And if it reboots, the phone is gonna be stuck at boot screen, at login screen, where I need to put the PIN and nothing works. I'm gonna miss phone calls. I'm gonna miss device, alarm clocks and things like this. So that's of course not gonna fly, and that's why we moved on different things, which I'm gonna explain in next slides, of course. One important topic here is, what if the user changed the password and changed the PIN? This is not a problem in practice. Why? Because there is key X that protects the full disk encryption, and key X is unlocked by the password. Okay, so if the user changed the password, key X doesn't change. The maybe encrypted version of X is changed, but X itself is not changed. Okay, so that's why if you change the password, you don't need to re-encrypt all your device, and that's why it's so fast. Okay, you can change password, nothing bad is going to happen. Okay. Okay, so moving on this full disk encryption, which had some problems, for example, alarm clock, so you miss phone calls and so forth, we moved on to file-based encryption. And in file-based encryptions, files are encrypted with different keys, and each of these keys can be unlocked independently. And so the idea is that apps can work in a limited context before being fully unlocked. And so you have context of partial lock, let's say, where you can do something but not everything. And it also makes work profiles more secure, because there is not only one boot time password, but potentially you can have several, because each file is encrypted independently and potentially with different keys. And one problem with this file-based encryption is that file-based encryption would encrypt the file contents and names, but it will not encrypt other information such as metadata. So for example, it will not encrypt the directory layout, the file size, the permissions, the timestamps, and depending on the scenario, this could leak private information, and that's why it's seen as a con. So metadata, it was not encrypted. So Android 9 kicked in with support for metadata encryption, and so this problem was solved. And this aspect of Android 9 basically would encrypt whatever is not encrypted by the file-based, I think is a typo, file-based encryption. Okay. The cons is that it needs hardware support, but recent phones all have it, so all is good. Another thing that is important is direct boot, and it's somehow related to data encryption. Basically, when you are in direct boot mode, so direct boot mode is defined when the device is powered on before the device is unlocked. Okay, so if you boot the device from scratch, and basically your phone is going to be locked at the please put your PIN, we call this mode the direct boot. Okay, and now basically apps can define at the PI level 2 different locations to store data, and one is credential encrypted storage, and which is decrypted only when the user logs the device. So again, credential encrypted storage. Credential, we are referring to the user password. So we encrypt things with some keys derived by the user password. So unless you put the password, your data is not going to be decrypted. And that's why credential encrypted storage is decrypted only when the user unlocks the device. And then you have device encrypted storage, which is somehow available both during direct boot and locked device. Again, device encrypted storage means somewhere on the device there is a key, which is difficult to extract if you steal the phone, and that is used to encrypt this other portion of the file system. So again, recap, there are 2 different encrypted things, ways of encrypting things: credential encrypted storage, encrypted with the user password; device encrypted storage, if you boot up the phone, is this part is going to be, let's say, unlocked. So this part is going to be accessible from application to applications even before the user put the password. Once you put the password, you're going to be able to decrypt also the credential encrypted storage, and now the phone boots properly. Okay. And now it's up to the developer deciding, this part, for example, like alarm clock, is not extremely sensitive, so I'm going to just put only in the device encrypted storage, but not in the credential encrypted storage, so that if the phone reboots, my application is going to have access to this, alarm clock information, even if the user did not put the password in. Okay. Again, it's a trade-off. If you are super sensitive about your alarm clocks, well, maybe you should install an application that stores the information in the credential encrypted storage. But if your phone reboots during the night, you're not going to be woken up. Again, as many things in security, there is a trade-off, and that's the trade-off that Android developers did. They allow the developer of the third-party applications to take a decision. And again, the fact that this stuff is decrypted with the key in the device, which is not used by the, which is not coming from the password, doesn't mean it's insecure. It's still quite secure. Of course, it's less secure because there is information. So all the information conceptually, it's in the device. But of course, there is many mechanisms in terms of hardware security and so forth that somehow makes the process of extracting the device encryption key very, very difficult. Okay. Cool. All right. So another topic is, again, it's a lot of stuff, and it's getting a bit heavy. But that's the, I want to do my best in providing some kind of overview of all the different things. And if you zoom out of this slide deck, you're going to see many different things, and I hope that by the end of the class you're going to figure out, okay, there are many different components, and then this component affects this aspect of security, this other component, this aspect of security, and many of these are complementary. Okay. And it can be a bit confusing, a bit overwhelming, but as somebody would say, it is what it is. So let's get to it. So device admin and work profiles. There are some apps that are called device admin apps. An app can act as a device admin, or could act as a device admin. this kind of a device admin thing is being deprecated. But it's important to know it existed and it exists. Basically, a device admin app can specify security policies. For example, you can say there should be the password and there should be this minimum password length, things like this, or there should be strong encryption. And if you enable this device admin app, then basically these policies will be enforced. And maybe for a normal user, they're not very interesting, but these are useful for the business scenario, where a company somehow purchases a bunch of Android phones and then it wants to protect them and gives them to their own employees. And of course, they want to make sure that, for example, the password is enabled and so forth. Okay. And also, device admin app can do powerful things like wiping data, force lock, and so forth. And again, this stuff makes more sense in a business scenario where the phone is somehow also controlled by the employer and is provided to the employees, and they make sure that some properties are used or satisfied. Cool. If you have a device admin like this, device admin app like this, maybe the company would let you access to the work VPN. You can sync data and so forth. Okay, so somehow a company has the way to allow only a secure phone or a phone running this device app to access private information and so forth. Work profile is something similar. As I mentioned, device admin is being deprecated, and work profile is a similar thing, where basically Android now can support work profiles. You can create your own work profile, and this work profile is somehow a separated entity or a separated context in your phone. You can have the user profile, your personal profile, and the work profile, and in the company maybe have access to some settings in the work profile, which is isolated to the personal profile. Okay, so now admins app can manage the self-contained work profile, where you can have access to company related information and so forth, but maybe the personal profile cannot really access this. So somehow they are sandboxed. They use Linux for this and so forth, but you get the use case. They want to deprecate this super powerful device admin. Now they're going to have these profiles. The company maybe controls only this work profile part, but it doesn't control the personal aspect of personal profile of the phone. And again, you can have a policy where you can say, oh, my corporate apps are only allowed in this work profile, but not somewhere else. And again, malicious apps or untrusted apps on a personal profile really have very few ways of interacting or no ways to interact with the work profile. It's yet another barrier. For the 15th time, if you could fully trust the Android sandboxing mechanism, you don't need this work profile stuff, right? If you install application X from the store and you trust fully that this app cannot really read and steal information from other apps, you don't need this stuff. But of course, since there are bugs, we want to be more reassured that this work-related stuff is actually very well isolated. And that's why we come up with work profiles. And that's why we have different steps and different ways of enforcing properties, so that if there is a bug here, maybe these other protection mechanisms are going to save us from leaking in private information. Okay. Yeah. And so they are very separated and so forth, as I said. Again, work admins may have remote control over the work profile part of the phone. And the cool part here is that you have the personal part and the work profile part. And from the personal part, you cannot read stuff from the work part, but the vice versa is also the cool part. In a sense, now the employer who controls the work profile cannot just read arbitrary personal things of the user. Okay, so that's a nice privacy thing right there. All right, so this is I think the last part of this for today. And again, it fits under the security mechanism, so it's the last one, but it's quite complicated. I mean, it's not as simple as the other ones. So we can do this eyes open, and this is extremely interesting stuff, and it's good stuff. So I'm sorry if this stuff is getting a bit long and a bit overwhelming, but this is the last one, I promise. All right, eyes open, trust them. So First of all, my Italian nature comes out in a sense that so far I've always drawn the system, the entire system as user space and kernel space. I always had an horizontal line, and then below this we had the kernel space with the syscalls and things like this, or the Linux kernel, and then we had the user space with the applications, the frameworks, and so forth. Okay. And again, my very, 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 very thick Italian accent. I'm from Italy, and of course I have lied. It's actually much more complex than that. Okay. So, and now finally, I'm going to describe how the system really is organized. So before I describe how we can, have a better diagram of how the system is really implemented, let me quickly describe from a very high-level perspective what ARM Trustzone is. Basically, it's somehow a hardware feature, and without Trustzone, what you have is the CPU, and you have the memory and things like this, and then the CPU read from the memory, writes the memory, and so forth. With Trustzone, what we have is that now there are two modes of running. One we can call it the secure mode and the non-secure mode. And this can be implemented in different ways. One way of implementing it is that you have two different CPUs. One runs in secure mode, one is non-secure mode. Another way is that you have one only CPU, like described in this picture, where you have a bit in the processor, one of the processor registers saying in which mode you're running. Are you in secure mode or in non-secure mode? And the idea is that not only the CPU has this concept of secure, non-secure mode, but also other peripherals. And there are some peripherals, for example, the RAM, the memory. Memory, now you have memory pages, but then somewhere you have another setting, another bit that says, hey, is this a secure memory or non-secure memory? And the idea is that non-secure memory can only access, non-secure CPU can only access non-secure memory, while secure mode of the CPU can access everything. Okay. So again, the idea is that if you are in non-secure mode, basically you cannot access the secure memory. And this doesn't only relate to memory. You can have different peripherals. And for example, you can say that, oh, this peripheral, I don't care, is not super sensitive. So non-secure CPU can access this, but you can say, hey, this peripheral is extremely sensitive and only the secure mode should be able to access it. Okay. So somehow it's some kind of another layer of isolation, another way of another abstraction for saying, hey, you have two modes of being able to run in, and there is hardware support for this. There is a bit somewhere or two different things or two different CPUs that says you're running in secure mode or you're not running in secure mode. Okay. Now, this is a hardware feature. Let's see how the Android folks, or in general the community, is building upon this hardware mechanism to implement something that is cool. So here is an updated diagram. That's the horizontal line that I always had, and I always had below the kernel space and above the user space. Okay, so the lie kicked in when I said that's how the system works. Oh, you have your user space up and they talk to the kernel. Again, it's not that simple. I mean, this is what I described so far. So in the kernel space, you have the Linux, Android OS, and now we start calling it untrusted operating system. And on top of them, we add system apps, third-party apps, and we call them untrusted apps. Okay. Again, see how I'm putting in the same bucket third-party apps and system apps. So they're in the same bucket doesn't mean they're all in the same category. Doesn't mean the third-party app can talk to the system app. Whatever I said is true. I just hide complexity. But whatever I said before about sandboxing is absolutely true. So they are all untrusted apps, but somehow system apps are run with the user X or user system. Third-party apps, each of them is running different users, so they really cannot communicate. Okay, but the novelty here is that there's a new line, and again, that's the line that maps to the secure mode of the processor and the non-secure mode of the processor. I guess you guessed it right. What we've seen so far, we're talking about the non-secure world. Okay, so what I've said so far about, oh, you have your own applications, and then you invoke a syscall in the Linux kernel, and the Linux kernel does this, and then it replies. This is all non-secure world. Okay, whatever I said so far, it's always non-secure world, and that's how normal CPUs work. Again, with more recent CPUs, there is this concept of trust zone, and we can implement this abstraction where we have non-secure world and secure world. And what the beautiful part of this is that we basically have the analogous component on the right side that we have on the left. So in the secure world, we have a operating system, which we call trusted operating system. So once the CPU runs in the secure mode, again, the organization is the same. There is a kernel space and a user space. Kernel space, we have the trusted operating system, and in the user space, we have trusted apps or TAs, okay? Again, this has profound implications, and it's important to see how the two worlds interact, and more importantly, why the ARM folks of the Android developers or all the other people that follow this kind of organization went through the trouble of separating these things. So the first thing here is, let me move myself, is what kind of stuff do we run in trusted apps? Well, in trusted apps, we want to run apps that are extremely sensitive. And they're so sensitive that we don't want just them to run in system apps, but we want to run them really in a different category because they're extremely sensitive, okay? And we have different things such as the keymaster that somehow is a trusted app that handles cryptographic material, the fingerprint API, that is the one that processes your fingerprint data, which of course is very sensitive, or the confirmation API, which is a kind of complex API that is actually extremely interesting, that deals with the topic of UI security. So we're going to deal with it later on. Or there is also a DRM component, so data right management, so that, for example, if you watch Netflix on your phone, Netflix can download the thing encrypted, and they're decrypted only in this trusted app, the DRM app, so that is more difficult to extract the decrypted content of Netflix and somehow store it and forward it around, okay? So again, if everything worked fine, if there were no bugs, this secure world and non-secure world would be useless, okay? We could use everything as a system app and everything is fine. But in a world where there are bugs and there are attackers that somehow can maybe modify also the non-secure world and put a custom kernel, maybe you have some components like the ones I've listed here that you really want to step up the game and you want to make really difficult to tamper with, okay? For example, the case of DRM. The scenario that is problematic, for example, for Netflix is that you download the Netflix content encrypted, and then the attacker has control over a phone, so he can put some kind of custom version of Android and read the decrypted content. So what this trusted world and secure world is trying to do is that there is a different level of security, and it's very difficult to achieve control there. So the way it works is the following. I've described about this unlocking and so forth. You can put custom version of Android. So the first security feature is that you cannot put a custom trusted OS. You cannot put trusted applications there, okay? So you can only put, in terms of secure world, you can only run in secure world things that are signed and validated by the chain of trust, okay? So there is no unlocking that kicks in. You cannot unlock anything. You can unlock the non-secure part, and you can do whatever I discussed so far, but you cannot unlock the secure world. So unless you're one of these manufacturers, there is no way you can push a trusted OS, a custom trusted OS, or a custom trusted application, okay? So basically now, even if you control your phone, even if you have root on your device, you have these DRM apps, DRM app running as a trusted app in the secure world, and even if you're root, you cannot really tamper with it and modify it, and that's where the security kicks in. So a place where a device, even if it's compromised, you really cannot just push something. Oh. And that's the first thing, okay? The other thing I want to discuss is, if this is a different world, how is the non-secure world or untrusted apps supposed to interact with them? Well, the way it works is that there are some APIs, and these APIs somehow communicate through, of course, some syscall, in this case, IOCTL. And again, there is some kind of driver interface so that the untrusted OS can relay some requests from untrusted apps to the trusted OS. And the trusted OS is going to communicate with the trusted app, and the trusted app is going to do whatever it needs to do and reply appropriately, okay? But again, there is no specific direct step from untrusted app to the trusted app, or from untrusted app to the trusted OS. Okay, and that's where the security kicks in. Okay, it's much more, there are some parts of code that are not even reachable by the attacker, and so it's more complicated to exploit them. The other thing here is that, only the untrusted OS can talk to the trusted OS. And of course, I need to move my face again. Most inopportune place. Okay. The key point is that even if the attacker compromise completely the untrusted apps and untrusted OS, or not compromise, but even if the attacker is the user itself and can push a custom version, this key master, fingerprint, and so forth are secure even if you compromise this. Okay. And the idea is that even if you bug here or a bug here, these other parts still resist. Okay. The other concept that is important is that you could say, sure, this is a different component, trusted OS, but somehow the untrusted OS keeps being able to communicate. So, as there are bugs in untrusted OS, there could be bugs in a trusted OS. And you will be right. There could be bugs in a trusted OS. There could be bugs in trusted applications. However, what the developers and so forth did was that the interface between untrusted OS and a trusted OS is much, much smaller with respect to the other interfaces. So the trick is that the trusted OS really exposes a very limited set of potential syscalls or services or whatever you want to call them. And since they are a small number, it's less likely that there are bugs there. Not impossible, but it's less likely. With respect to maybe Linux, which is a monster. It's gigantic and there are many bugs there. Okay, so the idea here is to reduce the attack surface, one, having a small, as small as possible surface where basically untrusted apps and non-secure world components can talk to the secure component. And the other thing is that you want this interface to be as far as possible from untrusted apps. So if you had an untrusted app or a malicious app on your phone, to compromise a trusted app, you will need to compromise the Linux kernel, from there's the trusted OS, and from then a trusted application. So there are multiple steps. Again, this is more about the defense in depth concept that I keep mentioning over and over again. Okay. So again, bugs are less likely. It's more difficult to find them. If you find them, it's more difficult to exploit them, and so forth. But again, as I said before, if you were wondering, oh, but there could be bugs there in trusted OS as well. Again, you are right. Sometimes there are bugs. They're rare, but sometimes they're there. And these bugs are extremely interesting. And I have a friend that with a couple of our friends in my previous school in Santa Barbara, they found bugs like this in the trusted OS and in trusted applications. And this friend of mine, Mike Pizza, basically had a super nice presentation on the details on how he found this bug with other colleagues and how he exploited it. And it's actually quite funny because one of his target for this exploitation was to exploit the fingerprint API, the fingerprint trusted application, so that the fingerprint trusted application basically kicks in whenever you put the finger on the fingerprint sensor, and it says, okay, this fingerprint is valid, please unlock the phone. So he tried to attack that one. And in terms of proof of concept, what he did as a live demo, as you can see in the link here at this minute, he basically tried to unlock the phone with his nose. So no matter what kind of fingerprint you would put, he put his nose and the phone unlocked. So quite entertaining, kind of a showman, and then it was extremely cool work. But again, that's just one of the many cases where people found bugs in Trojan. Okay. All right. So I think this is the last slide I have, and that's basically another small slide that I had before, where I described verified boot. It's slightly more complicated, and this slide shows how the Trojan component kicks in. So the way it works is that we have the bootrom, as I showed before, and then we have this BL2. These are different levels in the bootloader chain. And at a certain point, there is a component that starts a boot. And this a boot is what we've seen before. So from a boot, then there is a check, is the bootloader unlocked? And then if it's unlocked, you can load the custom Android kernel, otherwise no, or custom boot partition and so forth. If it's locked, you need to have everything trusted. But you see, there is another component now in the secure world above the horizontal bar, and there is no locking and unlocking there. So there is this BL31 point that basically starts the trusted OS in the TZ partition, and which usually is encrypted. And then this TZ partition starts specific peripherals, such as the radio. So basically, it boots, take the code from the radio partition and it boots it, and then it also starts the trusted applications. And again, as you see from this graph, there is no, from this diagram, there is no real check for, oh, is the bootloader locked or unlocked for the secure word part. So unless you're one of the manufacturers, you cannot run your custom code there. Of course, there are ways to play with it. So there are, there are different versions of these trusted operating systems. There is, I think, Trusty, which should be the trusted operating system that is run in Android, the ones developed from Google. But there are open source trusted operating systems. One of them is called Opti. And again, you cannot really run Opti on your Pixel if you bought it, because again, there is some kind of cryptographic checks. But you can buy boards where the bootloader is unlocked also for the trusted part. Again, these are more developer boards, and so you can basically flash trusted, or you can basically flash Opti there and play with it. And again, it's open source. You can find it on GitHub, and it's extremely interesting stuff. All right, guys, that was quite long, but that's about it for today. Next couple of set of slides is going to be more about again Android system security, but today already we found we discussed a lot of material, so I hope it's not too much, and I hope everything is clear. If not, shoot me an email. As always, I'm very happy to reply, and that's it. So that's about it. Have a nice week, and keep having fun with the second homework. Ciao, ciao.